Next we have number 6. It has two parts. So let's see part A first. In this, a matrix has been chosen C in the matrix algebra Fn. Then using this matrix C, a function has been defined from Fn to Fn, and the function has been named D suffix C, dc. So what it does is that if we evaluate this function at an x, where x of course is coming from Fn, that means x is an n by n matrix over F, then that image is xc minus cx. So we have to prove that for any two matrices x and y in Fn, dc of xy is dc of x times y plus x times dc of y. Does this not remind you of the product rule of derivative? It is like that. I mean, it has that same structure. So let's solve this part first. The solution is pretty straightforward. So we straight away just simply consider dc of xy. So by definition, that is just xyc minus cxy. And then what we do, we introduce extra terms. We write plus xcy and minus xcy. And then what happens, from the first two terms in this new expression, we take x common out using the left distributive law that we have in the algebra Fn. So doing so, we get x times yc minus cy plus, and then from the last two terms we take y common out using the right distributive law and a few other laws that we have in our matrix algebra. So doing that, we get plus xc minus cx times y. So you can then clearly see that this part is dc of y and this part is dc of x. So that way we get x times dc of y plus dc of x times y. And then we just interchange their positions to bring it to the form in which it is required. Okay, so that way we get this. One more thing that you have to be careful about here is that you do not just simply write, say you have this now. Don't bring y first. See, matrix multiplication is not commutative. Okay, so you have to keep that in mind. So that is part A. Next, let's see part B. Part B, two matrices are given again from Fn, A and B, such that AB minus BA commutes with A. That is, AB minus BA times A equals A times AB minus BA. And then Q of x is a polynomial over F. So it's coming from the polynomial ring. If so, then we have to use the previous part, part A, to prove that Q of A times B minus B times Q of A is Q prime of A times AB minus BA, where Q prime of x is the derivative of Q of x. We have already seen the derivative of a polynomial in field theory. Okay, so let's see what the solution is. Okay, so this is how we start the solution, by calculating dB of A square. By using part A, that becomes, because A square is A times A, so this is dB of A times A plus A times dB of A. Now dB of A is simply AB minus BA, so here also we put that. And then we recall that AB minus BA, it is given that it commutes with A. So this product will be equal to this product. We can interchange the factors. So that way we get the same thing 2 times. So 2 times this. And then again, in place of AB minus BA, you write dB of A, say. So you get this fact. dB of A square is 2A times dB of A. Note one thing, that it's almost like differentiating A square. Something like that, because the form of the result is just like that. 2 comes down and A square becomes A, and then again you differentiate A with respect to, I mean, it's something like the chain rule. Okay, something like that. Next, say we calculate dB of A cube. So A cube, you can consider A cube as A times A square. Actually, you can write A square times A also. You ultimately will get the same thing. But anyway, let us first consider a times a square. So on that, if we apply dB and you use part a, then it will be a times dB of a square plus dB of a times a square. Now we have already calculated that, so we put that here, 2a times dB of a. What allowed me to change this order here? Note that dB of a is ab minus ba, which commutes with a. So automatically it will commute with any higher power of a as well. In particular, it will commute with a square. So that permits me to write like this. Then it becomes 2a square times dB of a plus a square times dB of a. So 3a square times dB of a. So you can see that a pattern is emerging. So you can guess what will happen if you apply dB on a to the power n. So let's see what that is. So in general, we have this, which we have guessed from these patterns, that dB of a to the power n is n times a to the power n minus 1 times dB of a. Okay, and you have to prove this. This is only a guess. Always remember, no matter how likely something may seem in mathematics, unless you prove it, you cannot be sure. So I leave the proof of this fact to you. It's a very simple, straightforward induction argument. Okay, so let's accept that this is true. Now we go back to that polynomial which is given to us, qx, and say we consider that the polynomial is this, where the coefficients ai obviously are coming from the field f. Okay, now what can we do with this? So now we have to consider that expression q of b times a minus a times q of b. Was it this or the other? No, it is that q of a times b minus a times q of b times q of a, sorry. Okay, anyway, we are now going to consider it and let's see if we get what we want to get. So we start with that expression q of a times b minus b times q of a, which is nothing but dB of q of a. Now you write q of a, that is, you substitute a for x in the polynomial qx, which gives you this. Note that here you cannot just simply write a naught or a 0, or even if you write, you have to understand that actually you are considering the scalar matrix, all whose diagonal entries are a naught, because it is a naught multiplying the identity matrix by a naught. That's what a naught means here. Okay, now in the very next line, it seems like we have simply taken dB inside and applied dB on each power of a. Is it possible? Well, it is possible, provided dB, that is our function dc, in general is a linear transformation. It is actually, and it's very easy to see why. You just go back to the definition of dc or dB in this case, same thing essentially. You will see that it is in fact a linear transformation. It's pretty straightforward to show why it is so. So that I am leaving to you to see. Okay, so this line is justified, and then in the next line we apply that guess that we have guessed, which you have to prove by induction. By that, dB of a to the power n becomes n times a to the power n minus 1 times dB of a, and accordingly the other things also get put in their places. What is this last dB of 1? By the definition of dB, this is b times 1 minus 1 times b, which vanishes. That means it's the zero matrix, so it doesn't stay. From the rest of the things, we can take dB of a common out, and if you do, you are left with a polynomial expression in the matrix A, and that polynomial is actually nothing but the evaluation of the derivative q prime of x at x equal to a. Okay, so you can clearly see that if in place of a you write x and write the polynomial, n times a n x to the power n minus 1 plus n minus 1 times a n minus 1 x to the power n minus 2 and so on. So that is nothing but the derivative of q of x. So that way we get q prime of a times db of a, and db of a of course is this, so that way we get our result. And let me just end the video here itself. It's becoming pretty difficult to make longer videos, and I'm also not getting enough reason to do that. So let's just end it here itself, and tomorrow we have analysis. So see you tomorrow with that. Until then, this is me, Lucifer from a mathematical group. Have a nice day.